Welcome to Essential Problems with Crip. In this series of videos, we're going to lay the groundwork for Lewis structures and take sample types of all the problems that are provided on your handout. Let's begin with the equation that's at the top for lattice energy equal to some kind of constant. We don't care about the constant. The constant's constant. Times the first charge times the second charge divided by the radial distance between them. So this is very similar to the electrostatic equation. This is in reference to lattice energy. So what's lattice energy? Well, coming off the last unit, you were working with the creation of ions using ionization energy and electron affinity. So if we take a sample problem from the previous unit, lithium atom in the gaseous state, fluorine atom in the gaseous state, we can produce lithium ion in the gaseous state plus fluoride ion in the gaseous state. But this process is not complete. Until those ions are brought together in a lattice formation, they are just simply in the gaseous state. And so the next movement would be to bring lithium gas plus fluoride gas together to form LiF solid. And that is the formation of a salt. And this is the energy that must be released for this process to occur. That corresponds to the strength of attraction between those ions is called lattice energy. And that's going to be always exothermic, of course, because we're purely bond forming here. We're bringing two charges together. So this is playing off of that. And what we're going to be doing in this first part is actually drawing Lewis structures for ionic compounds. And this is going to be pretty easy because, well, it doesn't get any easier than this. So if we imagine here, right, lithium in the gaseous state, we can represent its valence electrons. Of course, lithium only has one valence electron, and we can just represent it with one dot, right? And fluorine, right, if we look on the periodic table, has 7 valence electrons. And so using our little method, we place the valence electrons around, and then we pair. And so what's really happening is lithium is losing one valence electron and fluorine atom is gaining that one valence electron. And in order to show the movement of one electron, we use a single barbed arrow. So notice not double barb, but single barbed arrow. So that one electron is being removed from lithium and is going to fluorine. And the result of this, right, is that we have Li, but it no longer has that one valence electron. So we give it a formal charge. So it lost that one valence electron. It now has a positive charge. And fluorine now gains that electron to become fluoride, right? So if I draw the electrons around this guy now, all of them are paired. And now, since it has gained an electron, we give it a formal charge of negative. It is not appropriate to draw a line between them because they are not sharing electrons. The only attraction that is formed is because of their opposite charges. And it's important to note that in visualizing this, that in the lattice formation, in its crystal lattice, this is going to be continuing and repeating on in all 3 dimensions. Meaning, if we were to envision this, really we need to envision this repeating lattice structure in space, 3-dimensionally, where you have all of these charges placed out in space, going back into the page, coming out of the page, going right, going above, below, going left, and it's endless sea of this lattice framework, okay, in which the charges are really structuring themselves, because lithium would repel other lithium ions, fluoride would repel other fluoride ions. So it takes this formation naturally to kind of maximize the attractions between them. And that's going to hold the whole salt crystal together. Now, what we can do at this point is compare salt crystals to other salt crystals, meaning the strength of that lattice is going to be dependent upon two things. One, the size of the charge, and two, the radial distance between those charges. So let's take distance first, because that's perhaps the simpler one to take. So if we look at, say, lithium fluoride, right, and compare it to, say, versus lithium chloride. Now, if you look on the periodic table, chlorine atom, the chlorine atom, has another shell of electrons, and so it's substantially larger than fluorine. So chloride will also be larger than fluoride. And so just for sake of our representation, you don't always have to do it, but if we're comparing, right, I want to visualize this definitely substantially larger. But if that chloride is substantially larger than fluoride, the distance between the charges there in that crystal is going to be larger. That distance is going to be larger. That means that that won't be as attracted to lithium fluoride. Okay? And we could also compare to, say, lithium bromide. Let's draw bromide even larger here. Right? And we could even compare, right, to lithium, trying to draw lithium the same size, but now iodide, right? This one's super large, okay? So this will have the weakest attraction, and lithium fluoride will have the strongest attraction, just by virtue of the size difference, and that creating a distance between the charges. And by the way, this helps to explain solubility, because generally speaking, the salts that have stronger attractions will be insoluble, and the ones that have weaker attractions will be more easily to get into solution. And that's why, according to your solubility rules, if you recall, chlorides, bromides, iodides are always soluble, but we left out fluorides, because fluorides are typically insoluble. Let's look at the other thing that contributes to the strength of lattice energy. If we look at, say, we're looking at size, we've taken, well, we can also look at differences in charge. So here we have lithium fluoride, but we could also imagine, right, instead of lithium fluoride, maybe magnesium fluoride. Well, magnesium fluoride, magnesium would have a 2+ charge, right? But that would mean that, of course, we'd need 2 fluoride ions for every 1 magnesium. But the attraction that the fluoride ions would have to the magnesium would be doubled, because that's a 2+ charge versus this is a 1+ charge. Again, we're speaking generally here, and you're going to see that from the data once we go back to looking at data in reference to lattice energy. But it's pretty clear as a generalization that magnesium, having this 2+ charge, will have this be almost doubly attracted in this lattice framework than lithium. And we can envision also the same thing with aluminum. So aluminum having a 3+ charge here, of course, would be attracted in the lattice to 3 fluoride ions, and I'm drawing it equally spaced. Of course, this would be in 3 dimensions, and it would be repeating in 3 dimensions, but it's okay to just draw one part of the crystal. But here, as we're envisioning this, aluminum having that 3+ charge, since it has 3 valence electrons and will lose those in becoming a metal ion, naturally, aluminum having a 3+ charge will have 3 times the amount of attraction to a fluoride ion versus magnesium's attraction to the fluoride ion versus lithium's attraction to the fluoride ion. We can also envision the not only plus, 2 plus, 3 plus here, right? We could kind of create this little table here where we have Li plus again, magnesium 2 plus again, and aluminum 3 plus again. But now change the negative charge, right? So instead of 1 minus for our negative charge, let's have 2 minus. So let's say oxide. So oxide, oxygen, if it were to be ionized, would gain 2 electrons. Of course, for lithium oxide, we need another lithium ion. So you can see, though, this oxide would be doubly attracted, right, to the lithium versus in comparison to the fluoride ion. How about this scenario, though? Of course, we'd only need 1 oxide to 1 magnesium ion. But this scenario would actually have 4 times the attraction, right? Looking at our equation, it would have 4 times the attraction, all other things being constant, in comparison to lithium fluoride, right? And if we draw oxide ion over here, we'd have to realize, well, we would need a bit more, right? So here I have aluminum 3 plus. I would need 2 aluminum ions, Al, and we can, I'll put another oxide here, right? We need 3 oxides to 2 aluminum ions, but as far as attraction is concerned, this would be 6 times as attracted to that lithium fluoride crystal, right? And that's going off of just the relative comparison due to their charge, right? When I say relative, that means we're just looking at that. Of course, there are other factors to take into account. Well, there's going to be size. Size is going to be important. There's also going to be other factors, but we're simplifying, and that really has to do with how ionic that substance is. And because there is kind of a range based upon its electronegativity. But generally speaking, this works very nicely in comparing the strength of the attraction between ionic charges. Let's take one more. Of course, we can envision again having Li plus, right? Magnesium 2 plus and aluminum 3 plus here. But then having a 3 negative charge. So let's take something like nitride. Of course, we could do polyatomic ions as well, but I'm running out of space. So I'll put N3 minus here. Of course, nitrogen would have to gain 3 electrons. And we can draw Li plus and Li plus again. And so again, relatively speaking, this would have 3 times the attraction compared to our lithium fluoride. Here, we could draw nitride here. Let's draw 2 of them. And we're going to have to fit magnesium 2 plus over here. And so, again, this would have 6 times the amount of attraction compared to lithium fluoride. And here, again, treating all other factors equal, our aluminum nitride in this kind of hypothetical crystal lattice, because aluminum nitride, there's some, whether or not you have a pure ionic attraction there. But if we're treating that according to our rules, then this would have 9 times the amount of attraction as our lithium fluoride. Till next time,